components of Earth's magnetic field. Once we establish that Earth has a magnetic field, and this also we know that it's neither horizontal nor vertical, it is variable. In fact, at different places it is at a different angle with the horizontal. So just suppose that at a place this Earth's magnetic field has the angle theta with the horizontal. This is Earth's field. Obviously, it's going to have two components, one along vertical and the other along horizontal. You see, you might concede, you might ask me, you might have a curiosity why this vertical component has been considered downward. You know, the Earth's magnetic lines of force will emerge from geographical south this way. Suppose this is Earth. So, magnetic lines will emerge and enter this way. So, you could easily say in geographical north, vertical component is vertically downward. Obviously, you see little inclined, it's not exactly vertical here along geographical north-south, but if you observe from this very location, it is vertical and vertically downward. In this magnetic south, you could say, here the magnetic field is vertically upward. So, in both the places, you could consider vertical component as either possibility. It could be vertically upward, it could be vertically downward. In the northern hemisphere, it's going to be vertically downward. In the southern hemisphere, near Antarctica, it's going to be always vertically upward. This is angle of dip. H will be here BE cos theta, and this vertical component will be BE sin theta. We have resolved the magnetic field in two components along horizontal and along vertical direction. If we take the ratio of the two components, you see, you'll find tan theta equal to V upon H. Here theta is the angle of dip, and you know this actual angle of dip will always be measured in magnetic meridian itself, because a freely suspended magnet will always rest along magnetic meridian. But now we put one condition, means that magnet which is freely suspended is confined to a vertical plane that is at angle phi with this magnetic meridian. In that case, H will not be effective, because H will always be in the magnetic meridian, and you are choosing a plane at angle phi with the magnetic meridian, then effective horizontal component is going to be H cos phi. Then in that case, angle of dip will be given by this relation H cos phi. But now in that vertical plane, you are not going to have actual angle of dip. This will be virtual angle of dip. You take the ratio of the two, tan theta upon tan theta dash. This is equal to cos phi. You see, cos phi is never going to be greater than 1. It is bound to be less than or equal to 1. When this is less than or equal to 1, obviously tan theta will be less than or equal to tan theta dash. You might say theta dash. This is one very important result. What is that? The actual angle of dip is always in the magnetic meridian, and whenever you choose for experiment some other vertical plane different from magnetic meridian, in that case the virtual angle of dip is always going to be greater than the actual angle of dip that is measured in magnetic meridian. Now, suppose you consider a vertical plane that is quite perpendicular to the magnetic meridian. Had it been at angle phi, in that case, H will be given by H cos phi. But if you choose a vertical plane that is perpendicular to magnetic meridian, in that case phi becomes 90. That means the effective value of horizontal component is going to be 0. And when you say there is no horizontal component, obviously what remains is vertical component. Now, in that vertical plane, and that very particular vertical plane, if you are going to suspend the magnet, that will be under the effect of vertical component only. Why? Because horizontal component has become 0 over there. So, this magnet will be subjected to vertical component, and this will rest vertically. In that case, if this is allowed to oscillate, the time period is going to be 2 pi root I upon mv. And already you know, if it is vibration magnetometer, there the magnet is allowed to be horizontal only, and in place of this vertical component we use horizontal component only. In vibration magnetometer, based on this principle, we can compare the magnetic moments of two magnets separately. And one more thing you have to remember, this is known as the top point, this is known as torsion head. Suppose you rotate this torsion head by angle theta 0, and this magnet rotates only by angle theta, then twisting on the way has taken place equal to theta 0 minus theta. And twisting moment in this suspension wire is going to be c theta 0 minus theta. Here this c would be known as, you see, c is pi eta r4 upon 2l. This is called twisting moment or twisting rigidity. You can find this twisting moment. For equilibrium, this condition would be necessary, mh sin theta. This must be equal to c theta 0 minus theta. This condition is going to be applied when you have rotated the torsion head by theta 0, magnet has rotated by theta, and the whole thing has received the equilibrium, then this formula must be applicable over there. And now finally, one theorem that you have to remember. We are not going to enter into the derivation. Suppose there are two perpendicular planes, vertical planes, and in that planes, the virtual value of angle of dip is theta 1, theta 2. Then actual angle of dip could be calculated by using this relation, cot square theta equal to cot square theta 1 plus cot square theta 2.